Hi guys, welcome back to Data Every Day. Today we're looking at a data set of Starbucks menu items, specifically drinks. There's a drink menu expanded.csv here, which I'm going to be using to try to predict whether a given drink is coffee or tea. Now it's more like whether a drink is tea or not, because there's some in here that are not exactly coffee, I would say, like some of these frappuccinos. But you can see there's a good number of Tazo tea examples. And so all of these are tea. And what we're going to try to do is classify whether a beverage is tea or not. Alright, so let's get into the notebook. I'm going to import NumPy and pandas just to work with the data. For pre-processing, we'll use the standard scalar and train test split function from sklearn. And then TensorFlow to actually build and train our model. And we'll use the confusion matrix from sklearn.metrics to analyze the results. Alright, so I'll import those and we can load in the data using pandas.readcsv. We can grab the file path right over here. The one we want is drink menu. Paste that in and then take a look. And we have 18 columns. Most of them are numerical. We have a few non-numerical columns, and one of which, the beverage category, is actually where I'm going to get the labels from. So I think first we should also check for missing values. So we notice, okay, there's actually only one missing value here. A single missing value in the caffeine column. So we'll come back to that. Actually, why don't we just fill it first, right? So fill missing values. So what we'll do, because it's only one, and because it's a numerical column, we'll just fill it with the mean of the column. So, data sub caffeine, actually called caffeine mg, is equal to the same column, but dot fill na, which allows us to fill the column's missing values with a given value. And the value we'll fill it with will just be the mean of the column. And we have a problem. So right away we see can only concatenate strings, not ints. And so the reason for that is because the mean function calls a summation over the values, right? But when you try to sum strings, you try to concatenate them. So it ends up concatenating all the strings, and then it finds the missing value, or it finds an integer value in there, and it realizes it can't add them together. So that means this is actually, if we look, it's an object column. This is not a numerical column. And when we have a problem like that, a way we can diagnose the issue is by trying to cast the column into a numerical type. So data sub caffeine mg dot as type numpy.float. And we should get another error, but we can see the value that's preventing us from getting a numerical column. So it seems like somewhere in here there's an entry called varies, and that's the same as a missing values for all purposes, because we need actual data. We can't just have varies in there. So what do? We take the column and we can apply a lambda function to it. Actually, we don't even need to. We can just use the replace function. That will replace varies with a missing value, numpy.nan. And you see that should work. You can't see it exactly, but now it has it replaced. So all we have to do is set that to be the new column. And now if we try to fill it, actually first let's try to cast it now. Oh, it looks like there's also one with lowercase. So at the end we can just replace again with a lowercase v. And now we'll try to cast it, and now it works. So we don't have to worry anymore. We've fixed those sloppy entries, varies and varies. Now there are missing values. So if we look back at the missing values now, data.isna.sum, you can see caffeine now actually has 23 missing values. So that's still not too much to drop the column. We're just going to fill it with the mean. So that's what this will do. now, oh right, actually I didn't actually cast it yet. So data sub, here let me just grab this, equals the same column as type numpy.float. Okay, now it still has the missing values, but now we can fill it with the mean. Alright, and now if we look at the, here I'll print out total missing values, and we'll do data dot isNA dot sum to sum across the rows, and then sum again to sum across the columns. And we have no more missing values. Okay. Now let's create labels. So if we look at data, we have this beverage category column, and I want to take a look at the unique values in it. So beverage category dot unique. And you can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different categories, but this is the one we're interested in. There's a substantial number of them. I think it's something like 30% of them are Tazo tea drinks. And we want to know if a given drink is tea or coffee. So we're going to apply a lambda function to the column, beverage category dot apply lambda x. It's going to return 1 if x equals Tazo tea drinks, and otherwise 0. So we're going to create a new column out of this called t. And t is going to be consisting of 1s and 0s based on whether beverage category is equal to Tazo tea drinks or not. So we'll run that, and then when we're done, we're actually going to drop the original beverage category column. Oh, whoops. Because if you think about it, you keeping this column is like cheating, because it's complete. You can just predict if it's t or not based on having this column. All we have to say is if it equals that, we're t, and otherwise not. It's not t. So having this column here, since we created the labels from it, is cheating. So I'm going to drop that. Okay, and now take a look at the data. We now have 2 categorical columns. The rest is numerical, and at the end we have this labels column called t. And let's take a look at the class distribution. So I'll print class distribution, and a nice way to get it is you can print out just the t column, right? Dot value counts, which if you look at value counts, I'll just run this part of the code. You can see it shows how many of each are in a given label. We can actually divide that by the length of data, which will give us the number of examples. Or it's probably better to do data.shape sub 0. If we divide each of these values element-wise, that's what this will do, we'll get the percentage of each class. And so it actually looks like 20% of them are t's, and about 80% of them are not t's. Okay, but now we have proper classes, proper labels. So let's start encoding our features. So let's take a look. We just have these 2 columns that we need to encode, and maybe a little cleaning up over here. But let's take a look at these 2 columns. So beverage and beverage prep. I'm going to create a dictionary that's going to map a column to the length of the unique values in the column. So unique. So it's just going to map a column to the length of the unique values in that column, so basically the number of unique values in a given column. For column in just beverage and beverage prep. Oops. Alright, and you can see beverage has 33 unique values, beverage prep has 13 unique values. And because there's no ordering between these values, we're going to use one-hot encoding here. So I'm going to create a function called one-hot encode. And this is going to take in a data frame, a list of columns, and a list of prefixes. And we'll start by creating a copy of the data frame. And then for each column prefix pair in zip of columns and prefixes. So zip will pair up two lists element-wise into tuples so that we can iterate through them two at a time, like this column prefix. And then we can create a dummies data frame using pandas.getDummies for a given column with a given prefix. And what this will do is just create the one-hot columns that we need from the column, and so that each column has the prefix of our choosing attached to the column name. Alright, and then we will concatenate the original data frame and the dummies that we created next to each other, so side by side, axis 1. And we will drop, so df.drop, the original column from which we created the dummies, because it is no longer of use to us. Then we'll return the data frame. And that's a simple one-hot encode function. I think it's even easier to use than a lot of the like sklearn one. So all we have to do is say data equals one-hot encode, and we'll pass in data. We'll pass in a list of columns that we want to encode, which will be beverage and beverage prep. So beverage and beverage prep. And then we also need a list of prefixes for each of those columns. So how about we do bev and bevp. Bevp. Alright, let's run that. And now we take a look at the data. We can't see all the columns anymore, so I'm just going to go into the console and type pandas.setOption max columns none. And that will allow us to see all of the columns, and we can scroll across to see them all. Now you see we have all these one-hot columns at the end, but if we're just looking at the columns before the one-hot columns, you can see we still have a little bit more work to do. We have to worry about these percent signs. And so what we can do to deal with the percent signs, let me just say cleaning, say final cleaning. Alright, so we can do apply map here. So apply map is a lot like apply, but it applies it to every element in an entire data frame, rather than just in a column. And we can apply a lambda function that will take in some x, and it will return x dot replace. Oh, well, here we'll cast x to a string, and then we'll do dot replace percent sign with nothing. And then when we're done with that, we can turn it back into a float. All right. So we're taking any given one of these, any one in the whole data frame, turning it into a string, removing percent signs, then turning it back into a float after that, and we can store this in the new data. And we have an issue, which is could not convert string to float 3 space 2. And let's take a look at the data types. And I can't, if I run this, I'm just going to get this ... So what I'm going to do is, actually, instead of doing all of the data types, data.loc, all rows, but we're just going to do calories through t on the columns. That will give us a slice of the data frame just ranging from calories to t, because everything else is one hot column, so we don't need to see. So we'll get the d types of just those columns. We can see, okay, here we have these object columns because of the percent signs on these 4 columns. That's keeping them from being floats or integers. But we also have this guy. In total fat grams, we have an object column up here who really shouldn't be, because this looks like a proper float column. And then we notice one of the values, we forgot the decimal. And we could, it's not necessarily clear what's going on here. We could just drop this example, but if we take a closer look, we might be able to figure it out. So let's get a unique value list of everything in here. Total fat in grams, and I think there's actually a white space at the beginning. So I'm just going to grab that. So dot unique, And we can notice, okay, here it is, 3, 2. This is the problematic entry. Now, what is the range of these values? You see that most of the values sit around 1 or so, maybe like 1 to 10. This would be quite an outlier if it were actually 32. So I think it's safe to assume that this means 3.2. Right? We have 3.5, 2.5, 4.5, but no high numbers. The highest number here I think is 15. So I think we'll just make this 3.2 and that will deal with it. So all we have to do is say data sub total fat in grams dot replace 3 space 2 with 3.2. And there'll still be strings here, but that's perfectly fine. And we'll make that the new column. And now, if we try to apply the map, we should be able to, like the problem before was that we couldn't cast it back into a float afterwards because we had this thing that can't turn into a float. But now we turn everything into a string, replace percent signs with nothing, and then turn it back into a float afterwards. We should be able to do that. And now if you look at data, everything will be fully numeric and everything is floats, and there are no missing values. So we have a fully cleaned data set now. So let's do this. Splitting / scaling. So at the top I've imported the standard scaler from sklearn and the train test split function. And I'm going to use that to scale and split the data. What I mean by splitting is first we'll split the y column off from our x, which is y will be what we're trying to predict. Data sub t, right? Our t column is what we're trying to predict. So we put t in there. And then it's actually floats. Let's just make it an integer. As type numpy.int. And then .copy. I want to make a deep copy of it as an integer column. And then x is going to be everything except the t column. So we're dropping it from axis 1. And then we'll make a deep copy of that. Alright, so now y is just going to be the series of zeros and ones, and x is going to be all the data except the t column. And now we can scale x using a standard scaler. So a standard scaler will give each column mean 0 and unit variance, so that most of the values fall between -1 and 1. And x equals scalar.fit transform x. Alright, now if we look at x, let's envision it as a data frame. You can see it's a lot like before, but now all the values have been scaled. And now we can split x and y into train and test sets using train test split. So x train, x test, y train, y test equals train test split x, y, and we'll specify a train size of 70%. Alright, now we can begin modeling and training. So, let's take a look at our input shape. 61 features. So I'm going to start by creating an inputs layer with tf.keras.input, and the shape of our input will be a vector of length 61. Then I'm going to have two hidden layers, dense, fully connected hidden layers with ReLU activations, and here we'll pass in inputs, and I'll make another one, and here we'll pass in x, and then our output layer will just be another dense layer, but with one activation, which will be the probability estimate for the positive class, and this is sigmoid so that we get probabilities between 0 and 1. Then model equals tf.keras.model. We'll pass in inputs and outputs. Then we'll compile the model using an atom optimizer, binary cross entropy loss, and for metrics we can include two, accuracy and tf.keras.metrics.auc, which is the area under the ROC curve. Let's give that a name. Alright, and then we can fit our model and store it in history. I'll store the fit history in history. So I'll pass in xtrain, ytrain, and we'll give it a validation split of 20%. And how about a batch size of 32? And we can train for 100 epochs because I'm going to include a callback here that's going to stop the training. Sorry, equals. Okay. tf.keras.callbacks.early stopping will monitor a value, in this case, we'll monitor validation loss, val loss. And if the validation loss stops improving after 3 epochs, then we will stop the training and we'll restore the weights from the best epoch. Alright, let's run that and check the results. So let's evaluate the model to start. Model.evaluate on the test set, xtest, ytest. And you can see it's doing a fantastic job. In fact, this is extremely good. 0.999999 AUC, and we have a 97% accuracy. Let me include a random state here. I'm going to try, because there's such a small amount of data, the randomness here actually matters. I try 64, and I want to retrain, because I was actually able, to get 100% in accuracy and AUC. Now, given the length of the test set here is 73 examples, so this is saying we got 73 predictions correct out of 73, which I think is pretty good. But let's also get a confusion matrix. So first, let's get the true values, which is just going to be the y-test, but I want it as a NumPy array. And then the prediction values, ypred, is going to be model.predict y-test, x-test, So these are not the same. Model.predict x-test, if we look at it, is just these probability values. But if one of the values is over 0.5, then we can classify it as a 1. So if we ask this question as a Boolean statement, it's true if it's over 0.5 and false if it's under 0.5. And that's the same thing as saying 1 if it's over 0.5 and 0 if it's under 0.5 if we cast it into a integer. So we can make this into an array and specify dtype equals numpy.int to get integer values of 1 or 0 depending on if a given probability is over 0.5. Alright, so once I have those two, we look at them. Y_true looks like this, and predictions looks like, oh right, okay, so there's actually an extra dimension here. So I'm going to use numpy.squeeze to get the extra dimension off. Okay, now it looks just like ytrue. They both look very similar. They're both NumPy arrays. Now we can create a confusion matrix from ytrue and ypred, and we can take a look at it. Actually, why don't we okay, at the top here I'm going to import matplotlib.pyplot as plt and cborn as sns. And at the bottom here, I'm going to create a new matplotlib figure. Let's give it a fig size of 6 by 6, and then we're going to get a cborn heat map of the confusion matrix. I'll turn on annotations, give it a color map, and we'll turn off the color bar. Alright, then we're going to get some labels. On the X, we'll have predicted. On the Y, we'll have actual. Then we'll do ticks. X ticks will be a NumPy A range from 0 to 2, plus 0.5, so that we can get the ticks not a comma, so that we can get the ticks in the center of the boxes. And then I'm going to specify the labels, which will be positive, positive and negative. Alright, now the y ticks are going to look the same way, so I'll just paste that down here and get y ticks. And give it a title, confusion matrix, and let's show. Alright, so here's our confusion matrix. These are true positives, true negatives. This would be false positives and false negatives. So, wait, no, this is false negatives. This is false positives. Because here we're predicting positive and we got it wrong. Alright, but you can see we don't have any false positives or false negatives because we got 100% accuracy and AUC in both classes. Alright, so that will sum up today's video. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.